Hi guys, welcome to my YouTube channel Code with Abhi. In this video, we will cover JVM architecture. What are different blocks of JVM? It is very important to first learn the basic of any language, how internally any language architecture works to understand the basic of language. Okay, so first we will see the JVM architecture diagram and what are different blocks of JVM architecture. So as you can see, this is a basic JVM architecture model. It contains multiple section. I will just briefly explain you what are different blocks of JVM architecture model. This is our class file. It is generated from Java compiler from our Java file. This class file is loaded into JVM model. Okay. First we have class loader subsystem. Inside class loader subsystem we have loading phase. Inside loading phase we have three types of class loader: bootstrap class loader, extension class loader, application class loader. Then we have linking phase. Linking phase perform three operation: verify, prepare and resolve. And then we have initialization phase. Initialization phase is used to initialize static member and static variable of class. Then we have runtime data area. Inside runtime data area, we have multiple blocks. One is method area, then we have heap area, then we have Java stack area. Inside Java stack area, you can see multiple thread stack. So how many thread we have created? For a separate stack is created. Same for program counter. For each thread, one program counter is created. So consider we have created four thread. So four program counter register will be created. Then we have native method area is used to execute native method code which is developed in C++ or C. At last we have execution engine. Execution engine contains three major sections: interpreter, JIT compiler and garbage collector. Then we have another two sections: native method interface and native method library, which is used to convert bytecode into a machine understandable code. First, we will see how Java is platform independent. As you can see in this simple diagram, we have Java code.java file and we have Java compiler. What Java compiler will do? Java compiler will convert .java file into .class file, which is bytecode. And this bytecode will execute on any operating system or any machine which has JVM in it. Okay, but you can see here we have different JVM and interpreter for different operating system. So the JVM is platform dependent, but bytecode is platform independent. You can execute our bytecode generated from one machine and execute it on any machine which has JVM in it. Okay. Now let's see class loader subsystem. The process of reading binary data of a class and converting into a Java class object in memory. What does it means? When we consider our class file, it will load it into a class loader subsystem, and class loader subsystem convert our class file into a class object which contains metadata of our class and loaded into a method area. This method area. Okay. And now let's see how how loading works. When JVM try to run our class file line by line from method area and find any class, it will then check if that class is loaded in method area or not. So what does it mean by that? So consider we have one class and it is dependent on some other class, like we are creating object of some other class in our class. So what JVM will do, JVM will check if that class is present in method area or not. If that class is not present in method area, then JVM will send request to class loader subsystem. This class loader subsystem work on delegation hierarchy. It means class loader will first send request to application class loader. Application class loader will not directly touch the class requested class. It will then delegate the request to extension class path, and extension class loader will then delegate the request to bootstrap class loader. So the first priority will always given to bootstrap class loader through application class plus to extension class. Then bootstrap class loader search that requested class in rt.jar file. Okay. If that class is found, then it will load it into method area. If not found, then that request will then delegate back to extension class loader and search the requested class in extension class path. If not found, then again delegate the request to application class path. If class found on any of the class loader, then it will load into method area, or else it will throw class not found exception. सो बेसिकली क्या होता है ना, सबसे पहले बूटस्ट्रैप क्लास लोडर पे जाता है और वहाँ पे सर्च करता है विद rt.jar फाइल. इफ नॉट फाउंड, देन एक्सटेंशन क्लास पाथ पे सर्च करता है विद विच इज प्रेजेंट इन lib एक्सटेंशन फोल्डर. और अगर मिलता है तो वो फिर मेथड एरिया में लोड करता है. अगर वहाँ पे भी नहीं मिलता है तो देन इट विल गो टू द एप्लीकेशन क्लास पाथ. सो अगर रिक्वेस्टेड क्लास मिलता है तो वो मेथड एरिया में लोड करता है ना, और प्रोग्राम विल स्टार्ट एग्जीक्यूटिंग from there onwards. If not found, then it will throw class not found exception. This is the functionality of loading in class loader subsystem. Then we have linking phase. Linking phase contain three process: verify, prepare, and resolve. Verification, what it will do, it will verify the dot class file with Java language specification and security content. In short, it will check if dot class file is proper or not, or it is modified or not. Then we have preparation phase. In preparation phase, static variable gets memory and it will assign with default value. If we have a class and we have any static variable, then it will memory will be assigned in the preparation phase, and it will be assigned with default value. Then we have resolution phase. Resolution phase is nothing but converting symbolic reference in the class to direct reference. So then after that we have initialization phase. In initialization phase, what will happen? Our static variable which will be assigned with default value will will then assign with the actual value which we set in our program, and the static block will get executed in initialization phase. So this is the overall functionality of a class loader subsystem. So now let's say runtime data area. The first block in runtime data area is method area. It includes all information of our class, like class name, fully qualified class name, interface name, its immediate superclass name, and modifier of that class or interface, like public, abstract, final. It also contains information about field, all the methods of that class, fields modifier name and type, and methods modifier name, return type, and parameter, constructor information. Also it stores the static variable with their values, because as static variable is a class level variable, so it is stored in method area only, and it is shared by all threads. It has nothing but the information of our class file, a complete class file. Now let's say heap area. Uh, So whenever we create object in our program using new keyword, the memory is allocated for that object in heap area, and also the instance variable get memory in that heap area, in that object only, inside heap area. Arrays and their elements are also stored in heap area. Garbage collector manages the heap area and destroyed unreferenced or unreachable objects. When object is created using new keyword, then only memory is allocated in heap area. So heap area is nothing but space where our object and its reference variable are stored. Then we have Java stack area. By default, main thread is already created in Java stack area and has its own stack. So this is Java stack area look like this. First one will always be our main stack, and how the number of threads created is equal to the number of stack created in stack area. Each thread has its own stack and will be destroyed once thread terminates its execution. So अगर अगर हम thread create कर रहे हैं, once that thread is created, उस थ्रेड के साथ एक स्टैक क्रिएट होता है इन स्टैक एरिया, एंड वंस थ्रेड एग्जीक्यूशन completed, that stack will also be destroyed. A stack is composed of stack frames, and on every method call, new stack frame is pushed on top of existing stack. So whenever any method get called from thread, consider main thread, so one stack frame is created here, okay, and execute that method, and consider another method is get called from that from that stack frame. Then another stack frame is created on top of that stack frame. Stack frame contains three parts: local variable, operand stack, and return variable. Local variable, what local variable contain is a primitive data type and reference to object. So whenever whenever a method execute a method, it contains some local variable or reference to some object, so it is stored in stack frame. Then operand stacks, like some operation are executed inside method, that also present in stack frame. And return address means if a method is get called from another reference object, so the address of that method will be stored in here. Okay. Program counter register. Each thread in Java application has its own program counter. It is thread specific and not shared among threads. So whenever any thread is created, a respective program counter is also created for that thread in program counter area. The program counter hold the address of bytecode instruction that is currently executing. So what will happen whenever any instruction is executing on that thread, program counter will hold the address of the current execution thread. If the current instruction executes, then program counter is updated to point to next instruction. So next, so program counter will now holds the address for next instruction. This program counter is critical for managing control flows Java, such as loop, condition, and method call. So, as it says, it is useful to manage the control flow of our program. It ensures that the correct instruction are executed based on program's logic. Okay. Then we have native method area. So, as you all know, Java internally has some native method. So, when this method calls, it managed by native method area. The primary function of native method area is to facilitate the execution of native method. When a native method is called from Java code, JVM uses the native method stack to manage the call and its execution. So consider we have we are calling one method which is written in native method inside Java. So that method execution is or manage is done by native method area. Now let's see execution engine. As you can see in this diagram, execution engine have three major section. Inside execution engine, we have interpreter, JIT compiler, and garbage collector. What is the use of execution engine here is it translates the platform independent bytecode, which is our class file, into platform specific machine code and manages the execution of this code. So once our runtime data area start executing our class file and perform our operation, then it will be passed to execution engine, and execution engine will convert that bytecode into platform specific machine code and execute that code that machine or in that operating system. So we have then interpreter. Interpreter will read and execute bytecode instructions sequentially. So whatever bytecode we get inside execution engine from runtime data area, interpreter will read and execute bytecode sequentially and convert into machine understandable code. This is efficient. Interpreter is efficient for small programs or the initial execution of large program, but can be slow for long running application, because what interpreter will do, one method which is executing multiple time, it will generate by machine understandable code repeatedly for that method call, for that repetitive method call. That's why it affects the program's efficiency. That's why we have JIT compiler. What JIT compiler will do, just in time compiler, the JVM identifies frequently executed codes. So there are like some of the frequently executed code in our application, and JVM will mark that code as hotspot. Then these hotspots are compiled into native machine code by JIT compiler. So whatever frequently executed code identified JVM, then this hotspot are compiled into machine native code. Once compiled, the native code is executed directly, provided significant performance improvement. Okay. Then we have garbage collector. Garbage collector is nothing but it is used to destroy unreferenced object present in heap area. So whenever any object use of any object is done and it has no use in our program, then garbage collector will identify this unreferenced object and destroy those objects. Then we have native method interface and native method library. Native method interface is connectivity between native method library, which is used to convert our bytecode into machine understandable code. Now let me show you the real example by creating one simple program and how any object is created in heap area and how any program execution happen through Java stack area. So as you can see here, I have created two class inside the same file name. One is employee class with the default value employee ID as 1 and name as test with the default constructor, and two setter methods for set employee ID and name, and two getter method for get employee ID and name. Then also I have created one test class which has main method and one print statement to check if a program started executing. Then created one local variable with the value as x just for uh, normal purpose. Then I have created one employee class object. Okay, employee class object e1 and employee 2 class object e2, and also print the value of both the class. Okay, now let me try to run this uh, application, run this class. First let me show you. We have only test.java file which contain both these classes, test.class file, test class file and employee class file in test.java file. And also there is another different program which is not our use. So let me first execute this program. You can see test.class file is created along with employee.class file is also created. Okay, now let me execute this program. Java test test. So here you can see our main method start executing, and also our both object will print its ID and value as one and test one and test. So how it is look in our uh, heap area and method area through diagram I will show you. So when our main method start executing, it will first print this statement. Then this local variable will get value inside stack frame in main thread. Inside Java stack area, one main stack thread will be created, and inside that stack frame will be created with x equal to 10. Okay, after that employee one object is created with the new keyword with reference variable employee one. So what happened in that mainframe, employee one object reference variable will be assigned here. Sorry, employee object reference variable will be assigned here with address 101. Sorry, this is employee one object. This is employee one, not employee two. This is employee one with address as 101. This is the address of object where our object is stored in heap area. So this reference variable points to the address which points to the object of heap area. So inside heap area, object is created with address 101, which contains employee ID 1 and employee name uh, as test. Okay, test first initially it will be test, and then we have method whatever method we have, it will be there setter method, getter method. Same, our employee 2 will be created with 102 and and with default value 1 and test and some methods. After that, what I'll do, I will uncomment this part and try to execute this command, run this program again. Okay, so now you can see our first object name will get changed and second object will be as it is. Okay, so what will happen in memory level, once our object will get created and memory is allocated inside main thread, and when we try to execute this setter method with reference with that first object reference variable, one frame will be created, set name, with the name equal to test, and this test will be assigned to the instance variable of that object reference. Okay, so this name will be now converted to test1. Okay, and then this set name frame will be destroyed after executing this command. Okay, so that's why first set name will execute, update our object, and then our second object will be like that. So that's why you can see our two object with different values. Okay, so this is how our program will execute inside JVM memory area. Okay, so whenever from now onwards, whenever you create any program, you should understand how JVM create object, how stack frame is created. So this is very important to understand Java completely. So I want you to go much deeper into it. Get your question, comment, write comment about your question. I'll try to reply it, and if there are like long topic, I will try to create another video in this topic only. So just go much deeper into this topic, because it is a very important topic in perspective to Java. Okay, also, if you like the video, please like, share, and subscribe the channel. Okay, thank you.